Okay. So, good morning, friends. Yesterday, I had discussed about the fundamental of NMR spectroscopy. Today, I will concentrate only on some chemical reactions. And you all know that there are two types of chemical reactions. One is conventional or the slow reaction, and another type is the fast reactions. So my lecture is based on some fast reaction, that is how NMR method is useful for studying the fast reactions. Now you all know that in recent years NMR technique or NMR spectroscopy is becoming an increasingly important tool for the studying of several biological and chemical reactions. Any types of protein folding can easily be studied with the help of NMR technique. Similarly, very fast enzymatic catalyzed reaction can also be studied with the help of NMR. Even very simple hydrolysis of methanol in the presence of sulfuric acid can also be studied with the help of NMR. And large number of isomerization reaction or cis trans conformation analysis can also be studied by the NMR techniques. Basically, if you want to know the most important application of NMR spectroscopy, so it is of course identification of compounds, molecular conformations, but if you see your course content, there is a unit that is called the fast reactions. So therefore, I am not concentrating on the identification of the compounds, but I am concentrating on the fast chemical reactions. That is of course kinetics as well as the dynamics is also important. That means you can also determine the reaction mechanistic pathways with the help of NMR spectral analysis as well as the line broadening, the NMR signal with the help of things. And of course, some slow kinetics, I will also discuss some of the slow kinetics like proton exchange rate, where offline NMR is suitable for that. But for very fast reaction, online NMR technique must be used, and of course some enzyme catalyzed reactions. Now in my first lecture you have seen that I have given large number of recent articles related to the role of NMR for monitoring the fast reactions. So here also I am showing one of the very good research paper published in ChemCom, which is a very important journal for the fast reaction technique. Of course, the online technique. Now, basically, the technique is based on the types of the reactions. Now, suppose you are performing an experiment where the half-life is, you see, 10 to the power minus 7 to 10 to the power minus 3 seconds. Very fast reaction. That can be studied with the help of relaxation time measurement. I will explain what is relaxation time measurement. In my first lecture, I had given some information about the relaxation time or the decay. But if the reaction is slightly slower, say for example, if the half-life is 10 seconds, suppose, or even 10 to the power minus 3 seconds, that can also be monitored by analyzing the variations in the resulting NMR spectral line. And of course, in both the cases, the reaction can be studied under the equilibrium conditions. You all are aware of the actual definition of the relaxation time. There is a perturbation in the equilibrium and then it's come back to your original position. And you are all aware of these different types of P-jump method or T-jump method or even stop flow technique. So, suppose this is an NMR magnet and that is the reaction NMR tube. So, if the reaction is very fast, just like your fast flow or the stop flow technique, we need special type of syringe pump so that the reaction mixture can be pumped directly to the NMR tube. That is the difference, and it is, I am taking these photographs from this very important research paper that is published in another very good journal, Nature Communication, in 2022. Very recent articles that how real-time monitoring of some fast reactions. So, if the reaction is very fast, reactions can be pumped from the reactors, you can call it the reaction vessel, to the magnet, and the progress of the reaction can be monitored online. At the end of the lecture, I will show some of the device by which a fast reaction can be studied. And another thing is also possible, that fast and continuous transfer of the reaction mixture from a reaction vessel into a glass flow tube located in the NMR probe. That is the one of the technique we will use. Now this is a very important point. How do you study the chemical kinetics? The measurement of the rate constant, because we are concerned about the determination of the rate constant. So, naturally, yes, you can monitor the resonance frequency, or sometimes it is called the Larmor frequency. You can monitor the, of course, chemical shifts, as well as you can monitor the relaxation rates. I will explain what is the relaxation rate. And as usual, it is a simple NMR spectra are characterized by, you all know, chemical shift or spin splitting, coupling constant, relaxation rates of the nuclei, spin lattice, and spin relaxation time. In my first lecture, I had explained the difference between the spin lattice relaxation and spin relaxation time. Today also I will just very briefly explain this, the spin lattice and spin relaxation time, because with the help of these two parameters, one can study the rate of the reaction, or you can determine the rate constant. So, this is also one of the most important research paper, and in my first lecture, I had discussed about the Bloch equations, and you know that for studying the chemical kinetics, the motion of the magnetic moment is to be calculated, and I have taken this complete derivation and the concept of this motion of the magnetic moment. Of course, it is based on this great Nobel laureate Bloch equation. So, if you want to study details of this technique, you must read this article, Rate Constant Determined by Nuclear Magnetic Resonance, and it is published in a journal. The name of the journal is Methods, and it is, of course, a very old research paper published in 2001, but this is very important and suitable to study the chemical kinetics by these methods. So now let me explain, let me derive this equation. So So there are two conditions. One is along with this external magnetic field, and second is in the plane perpendicular to the B0, that means X and Y plane. Let me just show you this. If you see this point, so this is actually Z direction, X and Y. So there are two conditions: rate of change of magnetic motion or magnetization with respect to time. So one is in the Z direction, another is the X directions. Now the change, the angular momentum is equal to minus B0 and M, that is the external magnetic field and the motion of the magnetic moment, or you can write the magnetization. Fortunately, the spin angular momentum is related to, or you can call it is the spin angular momentum is directly proportional to that magnetization. So if I equal, so there is a constant magnetokinetic ratio. So if I take the derivative of this, that means change of magnetization with respect to time, that is equal to, it is a constant. So rate of change of spin angular momentum with respect to time. Rate of change of spin angular momentum with respect to time. So now you substitute the value of dp dt in the above equations, because that is our equation. So we will get the value, final value is that rate of change of magnetization with respect to time is equal to gyromagnetic ratio, B0 and M. Everything is there. Now, most important part, that means when we place this sample in external magnetic field, you know that there is a flip, lower energy and the higher energy, and that is exactly equal to the radio frequency region. So therefore it is called the resonance. So when it resonate or absorb this radio frequency region, it releases that energy. Now there are two possibilities. One, that decay or the relaxation, the release of the energy in z-axis, and second, that the decay of the relaxation in the x and y axis. So that type of decay or the relaxation can be divided into two parts. And of course, both these relaxations are non-radiative transitions. So that means that part corresponds to two relaxation rates. One is spin lattice relaxation and second is the spin relaxation. And if you see this diagram, so you can understand that spin relaxation is the transverse direction, x and y directions, and the spin lattice relaxation is longitudinal. So sometimes it is called the longitudinal relaxation, it is called the transverse relaxation, and for studying kinetics we have to depend on the spin relaxation. That can be indicated as a T2 like that. Now it is one of the simple diagrammatic representation, external magnetic field and this time. So the spin lattice relaxation time quantify the rate of transfer of energy from higher energy level to the lower energy level it released to the other degrees of freedom. Maybe excess energy can be transferred to the solvent also. So therefore it is called the spin lattice relaxation. That means that energy is to be released to the surrounding of that nuclei. And of course, everywhere we follow the Maxwell-Boltzmann distribution. Everywhere we follow. It is the fundamental of the spectroscopy or any type of spectroscopy. Absorption of radio frequency region and the release of the energy. So everywhere, whether it is a longitudinal relaxation, but there is a restoration of the Boltzmann distribution. And if you ask me what is the range of this longitudinal relaxation time, it is 10 to the power minus 4 to 10 to the power 4 second for the solids. And for liquids, 10 to the power minus 4 to 10 to the power 10 second for the liquids. Similarly, for transverse relaxation, sometimes for liquids, the value of T1 is almost equal to the T2. So you can understand this thing, that relaxation time M0 starting point, and after that position is MZ. So in one direction. Now I am just showing the second direction, which is very important, that a decay in the transverse component, X and Y direction, you see this type of the things. So a decay in the transverse components with XY plane, exchange of the energy between the spin of the different nuclei. But of course, the energy must be equal. So it is not transfer to their environments, surroundings or the lattice. So therefore it is called the spin relaxation. So it is like that. And of course it is depending on this T1 also. And here the range is slightly different, 10 to the power minus 4 second for solids and 10 to the power minus 4 to 10 to the power. Sometimes it is, of course, for liquid it is T1 equal to T2, sometimes. Now just you listen very carefully that how this relaxation time depends on the chemical kinetics and rate and other things. So these relaxation processes depend on the time. As it is depends on the time, so naturally we can get the kinetic information. So it is, and according to the Bloch, this relaxation process, it is kinetically first order process, and the relaxation time is the time taken for the population difference to become 1 exponential of the original value. That means if you understand the actual relaxation process and the relaxation time derivation, so therefore I am just saying you that the Maxwell-Boltzmann statistics must be restored, because again it is the number of molecules and other things. Now how you correlate the NMR spectrum with that T1 and T2 values? I will of course explain the Heisenberg uncertainty principle, but before that you must know that if the T1 and T2 are small, if the value of the T1, T2 are small, the lifetime of excited nucleus is short. That is, immediately they return to their original states. So therefore, there is a broad absorption lines in the NMR spectrum. Again, I am just repeating these things. If the T1 and T2 are small, so naturally the lifetime of the excited nucleus is short. So we are getting some broad type of NMR lines. On contrary, if they are large, That means you can call it just before the reactions. So there is no relaxation or decay. So on contrary, if they are large, T1 and T2, so we will get the sharp spectral light. So on the basis of this T1 and T2, you can predict the nature of the conformation, whether there is a slow exchange or the fast exchange. And of course, the shape of the spectral lines depends on the T1 and T2. And this is based on the Heisenberg uncertainty principle. I am just coming to that point, that how it relates with that line. So you all know that this Heisenberg uncertainty principle, the delta E and delta T, H upon 2 pi. So the line width or broadening of the line of the NMR signal is determined by the lifetime of the spin state, as I have already mentioned to you. And we know that this E is equal to H nu, so there is a change in the energy, so therefore I have written this delta nu. So I can write like that, delta V, delta nu and delta T is equal to 1 by 2 pi. So now you can understand that if I write this delta T, so 1 by 2 pi delta nu, the Heisenberg uncertainty principle states that the product of the uncertainty, measurement of the energy and particular time, and it is inversely proportional. If delta E is very large, delta T will be less, lifetime will be less, approximately equal to H. How? Now just I am taken this information from a very good journal of chemical education. You just read it very carefully, that uncertainty principle states that the product of the uncertainty, this and this, in the measurement of the energy of a particular state and the uncertainty in the lifetime of the state. Because I have already told you that if the T1 and T2 value is small and large, it will, if the T1 and T2 are the small, the line will be broad. And if it is very small, so it can be explained like that. And same thing, delta E and delta D, H means H upon 2 pi, like that. Or I can write like that, delta is equal to H nu half. So that delta nu half, the absorption light width of the transition, is inversely proportional to the lifetime of the excited state. That means the same thing. So if one is high, another will be low. One is low, another will be high, lifetime. It depends upon the lifetime. If the lifetime is very low, sometimes lifetime is very high. So this initial state, there is no change in spectra. So an exact analysis of the line broadening product, suppose you are performing some experiment and you are getting such type of broad line, so you can throw some light, yes, there is no exchange. And of course, everything is based on that Bloch equation, that means change of magnetization with respect to time. Same without the Bloch equation. So the Bloch equation describes the motion of the bulk magnetic moment. So again we are coming to this same point, motion of the magnetic moment in a sample in the presence of a external magnetic field. Here they have written is H0, but we are using B0. So that is the actual reason for getting different types of signal. Now I am coming to the example. So I will show you one or two examples. First example is a very common example. It is available on all the books. That is dimethyl acetamide. Dimethyl acetamide. So you know that the environment is here different. Environment is different. And suppose after this isomerization, again the environment is here different, environment is different. So there are three possibilities. One is very fast exchange, and this exchange sometimes depends upon the temperature also. Within a fraction of a second, there is exchange. Another is the slow and intermediate exchange. And in between slow and fast, there is a coalescence, means mixing of these two, gradually this slow exchange and the fast exchange. So how do we study these three types of behavior? I am taking some of the research papers like that. This type of, it is a general, it is a specific example, dimethyl acetamide, and it is a general example, AH to BH. Again, it is a exchange type of the reaction. So the chemical shift of a nucleus change when the chemical environment around this changes. So in a molecule, this can occur either due to the chemical reaction or due to some conformational changes. So I am showing the one of the research paper of this scientist, Alex D. Band. And it is also very old research paper, but published in a very good journal. And from that research paper, I have used this NMR spectrum, published in the Progress in Nuclear Magnetic Resonance Spectroscopy. They have given three examples, slow and fast. Now you see. Now they have used, you see this azapropazone, this compound. And again there is a possibility of this rotation about the CN bond can interconvert the position of the two methyl groups which have different chemical environment. And it is depends upon the different types of temperature. So for example, suppose this is 223 Kelvin, then 243, it again 10, 253, 263, 273. So it is a temperature dependent reaction of azapropazone, derivative of course. And they are getting such type of peak. So if they follow this Bloch concept, so in first case, when the temperature is very low, they are getting very sharp. That means that lifetime is very high. So there is no exchange. As we increase the temperature, you see coalescence, and ultimately we are getting one thing. So that you can throw some light, yes, such type of thing will happen. Similarly, I am taking another example that is published in Journal of Chemical Education. And here actually, whatever we are seeing in the books of Kalidas or other things, the original research paper, a physical chemistry experiment. That is, again you see, same equation. The beauty of this method is twofold. First, dynamic aspects of the system which are at equilibrium can be studied. For example, the rate information can be obtained for virtual reactions such as cis trans isomerization of NN dimethyl acetamide. Dimethyl acetamide, you see here. Now, this is actually frequency, resonance frequency of one signal, nu1, resonance frequency of this. You know that again here also we are just using that Heisenberg uncertainty principle, position and the time and other things. So they are getting three types of things. In one case, there is a very clear cut slow exchange. Then gradually there is a coalescence and ultimately one. So this is actually original research paper of that paper. So first So again, what I have observed that again it is also temperature dependence. So in the NMR spectrum is a function of the difference in their resonance frequency of the rate of exchange. The effects of exchange at several temperatures on the line width. So I think it is low temperature and gradually they are increasing the temperature, and it is obvious that at very high temperature there is it indicates a very fast exchange. So concept is very simple, and I am using only one of the, because you are studying postgraduate level, for the examination point of view I am using the very simple type of the reactions, but there are other complicated reactions also, but most of the books they are using this dimethyl acetamide reaction. So it is also same thing, but the representation is different. Again, slow exchange, intermediate exchange, then the fast exchange. That means the clear-cut message is that if there is fast exchange, so gradually these two peaks disappears. And what is the reason for that? I have taken from the books of this Kalidas. Now it depends upon this. You see that this average lifetime, that is relaxation time. You can call it a relaxation time. So it depends upon this value of resonance frequency of these two peaks. I am taking original photographs. I am taking from that book by C. Kalidas. So it's actually same thing, but the representation is different. So therefore, I thought that I must use the original photographs of that book also. So again, you see that this different type of resonance frequency, and this line broadening is depends upon this difference of this average lifetime or relaxation time. So it depends upon the value of this resonance frequency, whether it is greater than this value or less than, or it is exactly equal. C part, there is a coalescence part, and in first part if you see the A, you see this value is naturally 1 by resonance frequency is very less than this lifetime. So naturally, so there is no relaxation process, and at high temperature, again you see the last change, this value is very high, lifetime is very high. So this is naturally, it is quite natural thing. Now suppose these are all not very fast, but the conventional reactions. But suppose the reaction is very fast. I am using the another method. Then normal, basically sometimes you can call it the offline measurement of the resonance frequencies, and this is not very fast reactions. But generally I have taken from this Kalidas book, it is Chemical Kinetic Method, Principle of Fast Reaction Techniques and Application. This book is available in our library, and there are a large number of examples, but I am using only one example, which is very simple. But there are other examples available in that book. You must refer some of the other examples also. There are some numerical problems is also there in that book. I am not showing that numerical problem. So that is called the offline type of reactions. Because I have done some reaction with the protonation of this hydrochloric acid, site of protonation. That is also not very fast reaction, but not very fast reaction. So no special technique is required for that. But if the reaction is very fast, rate constant is 10 to the power 9 like that, or even their lifetime is less than 2 seconds, then of course you have to design your NMR machine according to that reaction. So sometimes that is called the online type of NMR system, or so because you have to do the design, validation and implementation of rapid injection NMR method, and it is depends upon the types of the organic reaction or any types of the enzymatic reaction. So you can choose accordingly which nuclei will be suitable for such type of this study. But most of the laboratories, they are using that carbon 13 and hydrogen 1. But for some organic reaction, we need P31, fluorine 19 or hydrogen 15 reaction. So lastly, I am giving another example. It is also a very good research paper, and it is also published in journal Chemi Engineering Technique for 2017. Why I am showing this? Just to understand the technique setup, how that reactants are pumped to the NMR tube. So that is, title is Studying Fast Reaction Kinetics on Online NMR Spectroscopy. So you see, because you have already studied the fast reaction technique by the stop flow, temperature jump, pressure jump, or any femtosecond spectroscopy. So everything is same, Only thing is that it is magnet. Basically nowadays people are using the superconducting, low temperature superconducting magnet. There is a probe, NMR tube, console, computer, that is separate. But our system is that we have to set up a system like reactant A, reactant B, and then there must be some pump. So without any manual system, we have to pump that reactant in the, and then it can be monitored through the computer and other things. So now you can understand the principle is exactly same, but technique is slightly different. Now I am taking this graph from that same research paper, that they are using a very simple reaction, like as I told you, the esterification of the methanol. In our M.Sc classes, you have done some reaction, hydrolysis of the methyl acetate. Hydrolysis of methyl acetate. But here they are using the esterification of methanol using a microreactor. So you see the NMR probe head, sulfuric acid is the catalyst, temperature is 30 to 50 degrees centigrade, normal cases. So you see, just like a normal system, you are getting some concentration with respect to time. Here is also same thing. That is what they are trying to express, that any type of the reaction can be studied, but we need a special type of device so that we can pump that solution. Same thing with respect to time and mole fraction of the, which is the help of chemical shift, everything can be calculated like that. Thank you.